Hi everyone. So we're going to start our talk. Robert is a rising second-year graduate student working with Professor Jim Liu. Today he will be presenting on the research he did on Lie algebras and their branching rules with the Lie Art Mathematica program while he was an undergraduate at Vanderbilt University. Robert, you have the floor now.
Thank you. So, as Jem said, I'm going to be talking about the branching rules of Lie algebras and Lie Art 2.0 Mathematica program, and this is largely based on this paper that I recently published with Robert Fager and Tom Keppert, based on work that I ended up doing at Vanderbilt. So, just an outline of the talk. First, I'm going to give you some motivation. Why should you even care about branching rules? What are their relevance to physics? And then I'll go a bit into the representation theory of Lie algebras, what you need to know, what exactly is a Lie algebra, what do I mean by representation, what do I mean by branching rules, and how do we compute this? And then I'll talk about the Lie Art Mathematica program, both the original version, as developed by Robert Fager and Tom Keppert, and the upgraded version, Lie Art 2.0, that I worked on with them. So, in the motivation, there's a natural connection between particle physics and representation theory. You don't necessarily have to have a theory with a Lagrangian, but suppose you start with some Lagrangian. This is, in general, going to be invariant under some. And these naturally give you some symmetry group. Call it G. Now, an important application of these symmetry groups is to gauge the symmetry. In other words, we're making the symmetry local. And I know mathematicians hate that term, because what we're really doing is we're saying it's not a symmetry anymore. It's a redundancy in the way we're describing the physics. But importantly, when we do have a gauge theory like this, the fields transform in representations of the gauge group. I'll be more specific what I mean by representation later, but for now, just roll with it. So, in general, when we have these representations, we can break them down to smaller representations via things like spontaneous symmetry reading. For example, the Higgs mechanism takes the SU2 cross U1 gauge group of the electroweak interaction, and it breaks it down to the U1 of electromagnetism. And this induces, in some sense, a branching of the representation. Now, sometimes we would like to embed the standard model gauge group inside of some bigger gauge group, say SU5, SO10, E8. This is the general scheme that we follow for grand unified theories. And then once we've done that, we can make predictions by branching these representations back to standard model representations. And in particular, if the particles end up in the wrong representations, we know we did something wrong. So what all of this is telling us is we want to look at the branching rules of representations of Lie. However, I now want to make an argument for why we want to look at the representations of the algebras. Obviously, the first argument should be that it's correct. So the representations and branching rules of Lie groups end up corresponding with those of their corresponding Lie algebras. And in general, we denote Lie groups by capital Latin characters, and we denote corresponding Lie algebras by fractors. Now, while it is true that these correspond, there are certain subtleties. In particular, we sometimes have what are known as projective representations, which are representations that fail by an overall phase. But in general, as physicists, we're okay with this because in quantum mechanics, overall phases don't really change the physics. And so this, for example, occurs when looking at SO3 or SU2. SO3, the rotation group in 3 dimensions, and SU2, the special unitary group in 2 dimensions, have the same Lie algebra. But SU2 has the same representations as its Lie algebra. SO3 only has half of those representations. And the reason is because the other half are representations of spinors, and they're projective representations. But nonetheless, as you know, spinors are very important. Now, the other reason we want to look at the algebras is because they're easier. So Lie groups in general are differentiable manifolds. And if you've ever worked a general relativity problem, you know that differentiable manifolds are not an easy beast to deal with. Whereas a Lie algebra is a vector space. In particular, you can think about it as being the tangent space to the identity of the Lie group. And of course, this makes sense because the Lie group is a differentiable manifold, so there is a tangent space of the identity. So what this is saying is, as you know, vector spaces are very nice to deal with. So it's much, much easier to study the algebra than it is to study the group. There's also a more subtle reason why we want to study the algebra. And the reason is that experiments actually tell us a lot more about the algebra than about the group. And that's because many of the calculations that we do and then test in experiments like the LHC and whatnot are really done perturbatively. What we do is we're really turning the group into its generators with infinitesimal transformations, and we're looking at the Lie algebra. And so when we test this, we're not really making any claim about the global form, about the topological features that distinguish the group from the algebra. So as a result, in this talk, I'm really not going to be precise at all about distinguishing different groups with the same Lie algebra. In fact, I'm not going to mention groups very much at all. So what exactly do I mean by a Lie algebra? Now, I have already said that you can think of it as the tangent space of the identity of a group, but this relies heavily on already having a group. We can extract away from requiring there be an associated group by defining a Lie algebra to be some vector space over a field, equipped with a bilinear operation known as the Lie bracket, which satisfies the properties of being alternating and satisfying the Jacobi identity. Now, this may not necessarily be an intuitive definition to you at first. However, there are some simple examples that we can construct. The easiest example is just to take any vector space we want and give it the trivial bracket. In other words, given any two elements of this vector space, their Lie bracket is 0. And we refer to this as an abelian Lie algebra. And the reason is because if we took some vector space of matrices, then naturally we would associate the Lie bracket with the commutator. And if the commutator is 0, then we have a commutative vector space, and hence the name abelian. Now, we can also construct a slightly more interesting, which is the set of antisymmetric matrices with vanishing trace. And associated with the Lie bracket is the commutator, and this is a Lie algebra. In particular, it's the Lie algebra corresponding to SON, a rotation group in n dimensions. Now, you may be, at this point, thinking that the commutator is really the only thing that could be a Lie bracket. But in fact, why don't we take our favorite vector space, right? R3. Maybe it's not your favorite vector space, but it's my favorite vector. And R3, if I take two vectors in R3, I don't have a natural notion of multiplying those together and subtracting multiplication in the opposite direction. However, what we do have a notion of is a cross product. And it turns out the cross product precisely satisfies all of the requirements of a Lie bracket. So R3 with the cross product is a Lie algebra, and it's an example of a Lie algebra that does not have the commutator as its Lie bracket. Now we can also define what we mean by a subalgebra. A subalgebra of an algebra is just a subspace, and by subspace I just mean a subspace in the sense of vector spaces, which is closed under the Lie bracket, which is defined on all of G. Now, we can also talk about maximal subalgebra. So we say that a subalgebra is maximal if every time there's some chain like this, where the subalgebra is contained in another subalgebra, which is contained in the full algebra, either this intermediate algebra is the subalgebra or whole algebra. And we generally require that this maximal subalgebra be proper. Otherwise, the only maximal subalgebra you're going to have is the whole algebra, and that's somewhat boring. Now, the reason it's useful to talk about maximal subalgebras is because if an algebra isn't maximal, it's going to be maximal for something. And so you can always go down the chain of maximal subalgebras to get the algebra you want, the subalgebra you want. And it makes it a lot easier to list off all the maximal subalgebras, because otherwise, if you tried to list all of the subalgebras, period, you would get lists that became very, very large very, very quickly. Now, we can also define an ideal, which we'll call I. And so I, subalgebra of G, and we call it an ideal if this Lie bracket of I with G is contained in I. And what we mean by this notation of a bracket of two algebras is we mean that it's these set of all Lie brackets of elements of I and elements. Now, the idea of an ideal is essentially analogous to that of a normal subgroup in group theory. Now, similarly, we can define an analogous notion of simple as an algebra is simple if it's non-abelian, in other words, it's non-commutative, and it has no non-trivial ideals. And by a trivial ideal, I mean either the whole algebra or the algebra that consists only of the zero vector. And this is completely analogous to how we define simple groups. Similarly, we can define a semi-simple Lie algebra as being one which is non-abelian and has no non-trivial abelian ideals. Now, interestingly, semi-simple Lie algebras can always be written as a direct sum of simple Lie algebras. And in general, given any Lie algebra, we can write it as a semi-simple Lie algebra, semi-direct producted with a thing known as its radical. And it's not really important what the radical is, but what's important is that we can always reduce a Lie algebra into a semi-simple Lie algebra combined with something else. And this semi-direct product is just telling us that there's a non-trivial structure there. We're not just putting them next to each other, we're actually introducing a structure. But the specifics of this isn't important. The important point is that we can really, for the most part, reduce the study of Lie algebras to the study of simple Lie algebras. And this is important because simple Lie algebras are classified. And I'll get to this later. But very important to be able to study just the simple Lie algebra. Now, we can define something known as the Cartan subalgebra, which we'll call script H. And this is a nilpotent and self-normalizing subalgebra of the whole algebra. By nilpotent, we just mean that this lower central series eventually becomes zero, in the sense that for some n, hn is zero, and every one beyond that is, of course, also zero. And self-normalizing, we just means that h is equal to its normalizer, which is, again, the set of all elements such that this Lie bracket of G with H is contained in H. Now, if you've never seen this definition before, it's completely unintuitive. A way that it's frequently defined in physics papers is it's defined as being a maximal subalgebra of mutually diagonalizable, generated by mutually diagonalizable generators. But that I don't like that because that requires you either be working with a matrix Lie algebra or you've already introduced the notion of a representation. However, it does give us an interesting intuitive way to think about it, which is that it's the maximal space spanned by mutually compatible observables, in the sense of being compatible as quantum mechanical observables. Importantly, for a finite dimensional Lie algebra over some algebraically closed field of characteristic 0, in particular, our favorite one is the complex numbers, then the Cartan subalgebra is unique up to isomorphism, because that's really the best we can ask for, and it's abelian. In other words, it's commutative. And this is important because this tells us we can actually use the word z when talking about the Cartan subalgebra. And the abelian nature works well with our notion of compatible observables. Now, in general, we refer to the dimension of the Cartan subalgebra as the rank of the algebra. Now, once we have the Cartan subalgebra, this is very important as an element of the structure of the algebra. And we can take it and we can split the generators. And by generators, really they're just a basis for the underlying vector space. We can split them into the generators, which generate the Cartan subalgebra, and the generators that generate the rest of the Lie algebra. And we can set up the following eigenvalue equation. And this determines these non-Cartan generators, E alpha, and it determines these eigenvalues alpha I. And these E alphas form what's known as the Cartan Weyl basis, along with these HIs. And these alpha I's are known as roots. Once we have the alpha I's, since we have n Cartan generators, we can then assemble this into an n-dimensional vector by setting components alpha 1 through alpha n, and this is known as a root vector. And it's very common to refer to the root vector simply as a root. And these root vectors label the non-Cartan generators. Now, once we have the roots, we can decompose the algebra as a direct sum of the Cartan subalgebra with all of the root subspaces, where the root subspaces are essentially just eigenspaces. Now, the roots can be assembled together into a root system, and this is just a fancy term for the set of all roots. And the root system determines the Lie algebra up to isomorphism. Now, from the root system, we can select a positive root system, which we'll call phi plus. And this is just the set of roots such that, given any root, either the root is in the positive root system or the negative of the root is in the positive root. And given any two roots, if their sum is, or given any two positive roots, if their sum is a root, then their sum is a positive root. Now, the intuitive way of thinking about positive roots is that they correspond to raising operators in quantum mechanics. For example, if we think about SU2, and we specifically think about it in the context of angular momentum, we're going to have three generators, Jx, Jy, Jz, and none of these are compatible observables, so we expect there to be a one-dimensional Cartan subalgebra, and we'll just pick Jz to be the generator of the Cartan subalgebra. Then, as you know, we can construct J plus, J minus as raising and lowering operators, and J plus generates the positive root system for SU2. Now, we can also define a simple root system, which we call delta, which is just a collection of roots such that, given any root in the whole root system, you can write it as a linear combination of simple roots in delta using only integer coefficients of a single sign. In other words, all positive integers are all negative. And in general, G is going to have some number of simple roots that's equal to its rank, i.e. the dimension of its Cartan subalgebra. Now, once we have the roots, we can assemble them into Dynkin diagrams. It turns out that you can prove that the root vectors are going to come in at most 2 lengths and 4 angles. So we can construct a diagram by starting by putting one vertex for each simple root. And then we can connect the vertices with some number of lines that depends on what the angle the root vectors make with each other. If it's a 90-degree angle, then we don't put a line. 120 degrees, we put 1 line. 135 degrees, 2 lines. 150 degrees, 3 lines. And then there's 2 equivalent conventions. Either we can shade in the longer roots, or we can draw an arrow from the longer root towards the shorter root. And both conventions are used, but they're never used at the same time. And of course, this is possible because there are at most 2 lengths of root. Now, once we've created these Dynkin diagrams, they completely classify the root system, and hence the Lie algebra. And as a result, they end up and in addition to that, they show the structure of the Lie algebra in a graphical way. So this is some examples. In fact, these are all the examples of Dynkin diagrams, because it turns out that simple Lie algebras are fully classified. So there are 4 series of classical algebras. This AN series is also referred to as fractor SU n plus 1, and it's anti-Hermitian, traceless, n plus 1 by n plus 1 matrices. And this corresponds to a special unitary group in n plus 1 dimensions, which is n plus 1 by n plus 1 unitary matrices with unit determinant. And of course, the Lie bracket for all of these is going to be the commutator because they are matrix Lie algebras. Similarly, fractor SO2n plus 1 and SO2n are Bn and Dn. It turns out that their structure is actually quite different, even though they both correspond to the rotation group. Of course, SON is the rotation group, and this Lie algebra consists of, in this case, for SO2n plus 1, it's 2n plus 1 by 2n plus 1 traceless antisymmetric matrices, SO2n and 2n by 2n. There's also this other, the symplectic group, which preserves a certain antisymmetric quadratic form, and fractor SP2n is just, it doesn't come up as much in quantum mechanics, but it is an important group. However, there are also 5 groups that don't fall into this classical algebra classification scheme. And those are known as G2, F4, E67, E8, where these numbers denote the rank of the algebra. And again, these n's also denote the rank. It turns out, interestingly enough, you can also define 3, E4, E5 simply as following this pattern. You notice you get 1 less dot over on this tail over here on each of the e's. You can remove this dot and you get E5. You can remove both of these dots and get 4. You can remove all 3 of these dots and get E3. Now E3 isn't even simple because there's no connection right here. And E4 and E5 are going to be isomorphic to combinations of these classical algebras. And so we don't include them as exceptional algebras. You can also define an E9, but this ends up being infinite dimensional, so we're really not going to get into that. Now, once we have the Dynkin diagrams, there's a simple procedure for getting maximal subalgebras. Now, there's two kinds of maximal subalgebras. The first is regular subalgebras. These, in some sense, are just defined to be subalgebras which are easy to obtain. So we can either obtain non-semi-simple regular subalgebras or semi-simple subalgebras. Now, the way we get a non-semi-simple subalgebra is we just take one of these Dynkin diagrams and we remove a dot from it, any dot of our choice, and then add a U1 factor. And this will give us some non-semi-simple subalgebra. And the reason it's non-semi-simple is because U1 is not a simple factor. So for example, if we looked at A4, which is SU5, then you would have 4 dots. If we say remove the second dot, you would have 1 dot, connected dots, and then a U1 factor, which corresponds to SU3 plus SU2 plus U1, standard model gauge group. Alternatively, we can get a semi-simple subalgebra by removing a dot from these fancy extended Dynkin diagrams. Now, these extended Dynkin diagrams are defined in a particular way by adding an extra root labeled minus gamma. Obviously, you don't want to remove the minus gamma, otherwise you get back to what you started with, which is somewhat tautological and it's not very interesting. But you take these, you remove any dot of your choice, and you reinterpret it, and this gives you some new subalgebra, which is going to be a regular maximal subalgebra. Now, what you may have noticed is if you look at AN, if I remove any of these roots, I get back AN. So AN has no semi-simple regular subalgebra. However, there are also a second kind of maximal, and those are special maximal subalgebra, which in some sense are simply defined to be the ones that aren't easy to obtain. Now, so you can get special subalgebras by playing around with Dynkin diagrams, but you have to do it in very clever ways. And people much smarter than me have done this already and found entire patterns of these maximal subalgebras, as well as special cases of them. So now that we know about subalgebras, let's talk a bit more about what we mean by representations. So first, we can define what's known as the general linear algebra of a vector space. So given any vector space V over some field K, then the general linear algebra of the vector space is the algebra of linear endomorphisms of the vector. In other words, it's linear maps that take the vector space to itself. Now, since we know that if V is finite dimensional with dimension n, it's going to be isomorphic to k to the n, then we can think of GL of V as the space of k-valued n by n matrices. We denote as GLN of k. So really what this is saying is that the general linear algebra for a finite dimensional vector space is just n by n k-valued matrices which take the vector in V to another vector in V. Now, a representation of an algebra is some map that takes the algebra to the general linear algebra of some vector space, such that it's an algebra homomorphism. And that just means that we preserve the structure of the algebra. Now, the way to think about this is because GL of V can be thought of as k-valued n by n matrices, we can think of this as simply being a map which takes some element of the algebra, and it may be some abstract element, or it may already be a matrix, and it outputs a matrix that represents this, and that you can use in conjunction with other elements that have been run through this map in a way which retains the original structure of the algebra. So in particular, this is telling us that we can represent the algebra as a collection of matrices, which is usually how it's introduced initially in physics. Now, the way we generally label representations is we label them by their dimension, usually in boldface. And then, since the dimension is in no way necessarily unique, if there are unrelated representations of the same dimension, we will denote them by primes. So you might have a 5 prime, a 5 double prime, a 5 triple prime. However, if they're related by one being the complex conjugate of the other, we label them by bars. So you might have a 5 and a 5 bar. Now there is one special exception to this rule, and that's for the case of D4. Now, if you look at the Dynkin diagram for Dn, you notice that when n is 4, there will be 3 dots arranged symmetrically around a central dot. And so as a result, there's a certain threefold symmetry, which we call triality. And as a result, there are 3 interrelated representations which get labeled by V, S, and C, rather than the usual bars or primes. Now, it's important to note that a representation doesn't have to be an injective map. The best example of this is the trivial representation, which is where we just send everything to the zero matrix. Now, you may think that this is a very boring representation, but this is a very important representation in the context of particle physics. For example, we know that the electron doesn't feel the color force. So if we did an SU3 gauge transformation, the electron should just ignore it. What this is telling us is that the electron transforms in the trivial representation of SU3. And hence, unfaithful representations are actually important ones. Now, there might be a question that's nagging at you, and that's, well, you said I could put any vector space in here, and G itself is a vector space. So what if I look at GL of G? And in fact, this is a very important representation known as the adjoint representation. So, call a representation irreducible if it can't be decomposed into the direct sum of smaller representations. By a direct sum, all we really mean is if you take the direct sum of 2 matrices, then you get some block diagonal matrix. So essentially, we're saying that a representation is irreducible if you can't simultaneously block diagonalize all the generators. Now, typically we refer to irreducible representations as irreps. And given some subalgebra of G, we can define a restricted representation, which is the representation restricted to the subdomain H. Since rho is a map, we can restrict it to H. And this will, in general, be some representation of H. However, the representations of H are not necessarily the same as the representations. And so, in general, this is not going to be an irreducible representation of H, even if it is irreducible in G. So the way in which rho sub H composes as a direct sum of irreducible representations of H is known as the branching rule of the restriction. So this is the thing that we really want to be calculating. So once we have representations, we can define weight spaces in analogy to root spaces simply as being eigenspaces that satisfy eigenvalue equation. Technically, lambda i's are the weights, and the lambda is the weight vector, where lambda is lambda 1 through lambda n. But again, it's a common abuse of language to refer to the lambdas as weights, weight spaces, and this is completely analogous to what we did for roots. And we refer to the corresponding system of weights as the weight system. And it turns out that roots are actually a special case of weights. In particular, they're the weights of the adjoint representation, which, remember, is when we chose G to be the vector space over which we were representing. It turns out that this weight system fully classifies the representation, much in the same way that the root system fully classified the algebra. And moreover, these are simply eigenspaces, and so we can think of V as the sum of weight spaces, much in the same way that we could decompose the algebra as a sum of root subspaces. Now, we would like to also actually calculate the branching rules. So the key to doing this is these weights that we've just. So what you can do is you can take the weight vectors and you can set them as the columns of a matrix, which we'll call W. Then what you do is you want to project the weights of the original representation to the restricted representation via some matrix, like P. And this is known as the projection matrix. So this we can easily solve using a right pseudo-inverse. Now, of course, you can't necessarily do this just for any old set of branching rules. And the reason is because we're not always going to have enough information for this to actually give us a good result. What I mean by that is, for example, if you just take the trivial representation, you know the trivial representation is going to branch to the trivial representation. It contains the absolute minimum amount of information possible. You can't gain information. And so the trivial representation branches to the trivial representation, but if we do this, we're not going to get a projection matrix that projects for all weight systems. It's just going to tell us that trivial representation comes another trivial. What you have to do is you have to use what's known as a generating irreducible representation. This is essentially defined as the smallest irreducible representation, such that solving in this way gives you the full information. Now, of course, these projection matrices are actually not unique. There are many equivalent projection matrices that will give you the same results. It turns out that there's actually a procedure for reading the projection matrices for regular branching rules straight off of the Dicking diagram. And LIART is fully equipped to do that. But for special branching rules, we have to use branching rules for the generating irrep. So, to summarize what we've talked about with Lie algebras, we first began by taking the Cartan generators and using those to determine the roots, as well as the Cartan vial basis. And then once we had the roots, we used those to construct a simple root system, and this fully classifies the simple Lie algebra. Then we did Dicking diagrams from the roots, and these can be used to obtain maximal subalgebras. And the algebras can be represented as a collection of matrices. Specifically, it's a map to the general linear algebra over a vector space, but this is most intuitive to think about as matrices. And this allows us to obtain the branching rules by restricting the representation to a subalgebra. And in particular, we can define weight systems, analogously to how we define root systems, and use those weight systems to actually calculate the branching rules via the projection matrix. So, now that I've given you bare bones introduction to the algebras, I want to talk about the LIART Mathematica program, which is what I actually mainly worked on. So, the original LIART program was first developed by Robert Fager and Tom Keppert, and was first published in about 2015, though I think the first version was released in about 2012. And LIART just stands for Lie algebras and representation theory. And it can do a lot of Lie algebra calculations. For example, it can fully calculate all the root systems that we've been talking about, calculate the weight systems. It can also calculate tensor product decompositions. And what I mean by that is, given two representations, you can think of them as matrices. So you just take the tensor product of the matrices, and this will give you some new representation. And in general, this representation is going to be reducible. And so you decompose this as the direct sum of reducible representations, and this is what's known as the tensor product. And LIART is fully equipped to do this for you. LIART can also deal with Young-Tableau, which are useful for working with N. And originally, it could do a pretty decent number of regular subalgebra branchings, though there were some that were missing, and it only had a couple of specific special subalgebra branchings, which was the main weak point of it. So, just to give a little tutorial on LIART in case you're interested in using it, you can enter irreducible representations, for example, either by specifying the classification in terms of A, B, C, D, E, F, G. And so what we do is we use the irrep command, and this first bracket tells us the algebra. The second one tells us the dimension of the irrep. Alternatively, we can use the more familiar names of SU, SO, SP to specify which irreps we would like. We can also enter barred irreps with the bar command. We can also enter primed irreps with irrep prime of whatever you would like to prime. Now, the decomposition of tensor products, as I mentioned in the previous slide, can be done via the decompose product command. So, for example, you feed in some irreducible representation that you specify. In this case, we're feeding in the 27 cross 27 bar of E6. And so what you do is you just feed in all of the representations that you want to decompose, and LIART quickly just spits out the answer. And you can put in any number of irreducible representations in the tensor product you want. As you can see here, I put in 3 and Liart handle it. You could put in 4, 5, 6 if you want, and Liart will take care of it. Now, more on topic, we can also talk about branching rules. And so Liart has a command called decompose irrep that, given a particular irreducible representation that you want to decompose, and a subalgebra that you want to decompose to, it calculates the branching rule for that specific irrep. However, you may not necessarily want one specific irrep branching. You may want an entire table for an entire algebra-subalgebra pair. And in that case, you can construct what the branching rules table with this command. So for example, we have SU5 to SU3 plus SU2 plus U1, which is relevant if you were doing grand unified theories in like the 1980s. But here what we're doing is we're first specifying what in some sense, the parent algebra is, and then we're giving it a list of subalgebras to branch to. And here we're using product algebra to specify that we want SU3 plus SU2 plus U1. And we could also list more things in here, and Liart would give us a table for each thing that we listed. And then here we're specifying the maximum dimension. Liart has no limitations beyond those of your computer for finding irreducible representations. And in general, there's going to be an infinite number of irreducible representations. So you have to tell it when to stop. Now, Liart 2.0 is the program that I worked on with Robert Fager and Tom Kephart, and we recently published this. And so we upgraded Liart to Mathematica 12, but that's not a very interesting thing to talk about. So instead, I'm going to focus on the implementation of new projection matrices. So a number of authors have already documented the generalized form of various projection matrices for various different branching rules patterns. In particular, there's a very beautiful, I think it's about 1,800 pages long paper by Naoki Yamatsu, which is very helpful. And so we input these new forms of projection matrices for different branching rule patterns. And what we noticed in the process was that certain algebra-subalgebra pairs ended up having multiple branching rules. For example, E7 has 2 different ways it can branch to SU2, E8 has 3 different ways it can branch to SU2, and SU15 has 2 different ways it can branch to SU3. Consequently, we updated the interface to allow users to specify which branching rules in particular that they wanted. For example, in decompose irrep, if we wanted, say, the second branching rule for the 248 of E8 going to SU2, we would just put a 2 at the end. Now, you may have noticed that I did do an example of the 248 of E8 branching to SU2 already, and I didn't specify a number. And that's because decompose irrep is designed so that if you don't specify a number, it will just give you the first one. However, the branching rules tables, on the other hand, will give you all the tables if you don't specify. However, you can also specify that you only want one of the tables, if that is what you desire. So, consequently, Liart 2.0 can now find all the branching rules for any algebra rank 15 or lower, guaranteed, unless someone publishes something new. What I mean by that is any regular branching rule, period, we can find it. And there's quite a few different patterns of special branching rules that we have in a couple of tables in the Liart 2.0 paper that Liart can find the branching rules for. However, the reason why I don't say we can find every branching rule, period, is because in general, at high ranks, there tend to be random cases of special subalgebras that don't necessarily follow a pattern. For example, I believe SP246, which is a rank 123 algebra, has, I think, a E8 subalgebra or something like that. It just occurs randomly. There's no pattern. And consequently, those things that occur without a pattern, we really can't write code that will always be able to find it. And in general, the really high rank ones are not included even as special cases because I'm not comfortable putting out software that I can't test. And once you get to very high rank, the limitations of your computer become quite apparent. Here is a very lengthy table of all the different subalgebras up to rank 15 that Liart is able to compute. Now, obviously, I do not expect you to read these tables in detail right now, but it's just here to show you how many there actually are. And in particular, all of these tables are actually included in the appendix of Liart. I think it's about 350 pages of tables or so. There's also tables for SO32, since that's relevant for string theory. Now, you may be wondering, well, it is a computer program. How long does it take to run? So we benchmarked Liart 2.0 using an Intel i7-6700HU processor, 16 gigabytes RAM. It's an Omen 15 laptop. In particular, it's the one I'm presenting to you on. And we used exceptionals because exceptional algebras tend to take longer to calculate, so they're better to use for benchmarks. So you may think, oh, I'll just give it some ridiculously big EREP of F4. I'll see how it branches to SU2 plus G2. And it turns out that the 1,801,371 takes just a bit over 2 minutes, which surprised me, but it's good. Now, the 2,282,280 of E7 branching to the same subalgebra takes only a bit over 6 minutes. And similarly, we can look at the 6,696,000 of E8 branching to various. And I think the computation times are fairly decent, especially considering how large this irreducible representation is, and that E8 is a fairly high-ranked group. And at worst, it's only a bit over 20 minutes. Surprisingly, SP4 is the one you would think would be easiest to calculate the branching rules for, but it seems to take the longest. But overall, these computation times are all fairly good. But what I've noticed is that in general, the greatest limitation is the memory capacity of your computer. 16 gigabytes of RAM will last you maybe up to rank 15. Rank 15, you start getting trouble. So, just to conclude the talk, Liart now has significantly extended functionality. As I said, you can compute any regular branching rule that you could possibly want. You can calculate every pattern of special branching rules in these tables that I showed you. And of course, every special case is up to rank 15 is covered as well. As I showed you, the extensions have pretty decent computation times. So in conclusion, please feel free to download Liart 2.0. It's available at liart.hebforge.org, and it's completely free. So if you're interested, there's no reason not to try it. Thank you. That's my talk. Any questions?
Now we open the floor for questions. You can unmute yourself anytime. So I might have a question. So you have the program in Mathematica right now, correct?
Yes.
Do you want to give us more demonstration?
Yeah, sure.
Okay.
For example, if you say wanted EREP of SU5, 5, and simple. I don't know, what exactly do you want demonstrated?
I guess just the basics or whichever you want to demonstrate, honestly.
Okay, if you want to pose EREP of 5 to, I don't know, product of comma U1. I don't know, I guess I already showed that example.
I have a question about the algebra and the fields that you used to define the algebra over. So suppose the field doesn't have a characteristic of 0, then what changes happen? And why are we just considering fields of characteristic 0?
So I'm not entirely sure how fields of finite characteristic end up. For the most part, as far as I'm aware, fields of characteristic zero are the ones that we're most interested in physics, but I could be wrong about that. I'm not really sure how fields with non-zero characteristic end up changing things.
Any more questions?
Again, I have another question regarding the infinite dimensional algebras. So you said E9 could also be included, right?
Uh, so I'm not particularly familiar with E9. Um, I I know you can define the EN series. Where is it? So you can define the EN series just by
Yeah.
it always being these two dots and this dot, and then some
Mhm.
number of dots
In
uh,
between.
after that. So like this is E6, E7 is just one extra dot, E8 is another, E9 is just adding a dot over here, uh, and that can be shown to be infinite dimensional. That being said, I'm not very familiar with E9, E10, etc. So I'm
Yeah,
not really
I'm
sure.
just confused with how are we exhausting the classification? Like at what point do we say that okay, now we have exhausted all the possible cases?
Um, but I mean, you can show
Even
that.
for say for rank 15, how did we conclude or how does the program know that there's no more branching rules? Like what is the cutoff?
Well, so we know that there's no more. So we can classify algebras just by writing down any Dinkin diagram we want, and then we either show that it's consistent or inconsistent. I'm not super familiar with that process. As for saying that the art can do all the branching rules, um, what I should really say is it can do all the branching rules that we know of. In principle, if someone did
Hmm.
something
Oh, okay.
clever with uh, a, some Dinkin diagram and they showed that in fact there's a subalgebra that nobody knew about, then the art wouldn't know about it. Uh, so what I should really say is all all algebra up to rank 15 subalgebras that we know about, I have tested and implemented in the code. But if someone discovers some new subalgebra doing something clever, um, then it's not in there.
Also, there is a corresponding classification. So because you said that these rules have corresponding analogs for the groups as well. So I guess simple groups also have been classified. Like that's a huge project that mathematicians have done.
Uh,
And yeah, there's like sporadic groups and stuff like monster groups and stuff like that. I don't know why there are not any corresponding Dinkin diagrams or some peculiar features like that in the classification of Lie algebras. Or also if there's any connection between the two.
I'm not entirely sure. Yeah, I'm not entirely sure.
So then what are you hinting at regarding the correspondence of branching rules for the groups?
Oh, okay. So that's just that. So the branching rules for groups. Well, so
Hmm.
they if the group is simply connected, then the branching rules will be the same as those of the algebra. Um,
Hmm.
and I don't happen to know the proof of this off the top of my head. But the reason we work with algebras is because algebras are easy to work with.
Yeah.
And we can do these very nice things that I've talked about. I don't actually entirely know how you would go about doing this from a purely group perspective, like without ever talking about the algebra.
Any last minute questions?
Oh, thank you, by the way.
Okay, if there's none, thank you very much. And please don't forget to fill up the feedback form for a speaker, and you would greatly appreciate it. And you can also find the feedback form in the PGSS website. So thank you again, and have a great day.